All right. So today I'm going to be showing you how to solve this common calculus problem of optimizing a silo. So basically, we're given a certain volume that's like a standard volume, and then we're asked to determine what is the minimum amount of basically surface area we can have to contain this volume. So basically, we want to be able to store like a certain amount of a grain in a silo, and we're trying to use the least amount of metal basically for a real world application. So right here, I have the two things you're going to need to know for this, which is the volume of a sphere and the surface area of a sphere. So we start off this problem by setting up two equations, a volume equation and a surface area equation for this silo. So the volume equation of silo, I'll put a S, not to be mistaken with sphere. I should put like sphere, and then that one's also there. So basically, the volume of a sphere, or of silo, sorry, is going to be half of the sphere volume. So 2/3 pi r3 to the power of 3. And then we're going to add the volume of the bottom, which is going to be basically the bottom area times the height, which is going to just be pi r squared times h. Okay, and then I'm going to set up an equation for surface area. So the surface area equation is going to be surface area of a sphere divided by 2, which is going to be 2 pi r squared. And then we're also going to be considering the bottom of the silo as a part of the silo. So I'm going to add on another pi r squared for the area of the bottom. And then to determine the the height's surface area, if you will, basically we're going to be doing the circumference times height, which is 2 pi r h. I'm going to use a little h here just because I feel like that's easier to write. So now, if you'll notice, we have a difficult situation here because we have two variables. So we're going to pick one. And also, just to be clear, our volume is staying the same, so we can just think of volume as like 1 or just a constant number. And then we're going to basically be solving for what radius and what height of the volume, basically, or what fraction is each going to be to optimize it. So basically, and then we can compare those two things. So basically, we have to pick a variable. So I'm going to pick h to get rid of just because that seems easier. So what I'm going to be doing is solving for h. So I'm going to solve for h in the volume equation because volume is held constant here. So I'll just write it in red because why not? So the height through algebra is going to be v. I'm going to just say v is just the volume of the entire thing as an assumption, minus 2/3 pi r to the power of 3. And then we're going to have to divide by this part. So it's divided by pi r squared. So now what we're going to do, now that we have an expression for h, is we're going to sub this in the surface area equation for h. So we get rid of our h variables, so then we only have variables in terms of r. So on the next page, I'm going to write out the surface area equation now, except with our h plugged in. So that's 2 pi r squared plus pi r squared. I'll just say 3 pi r squared. Pi r squared. And of course, remember that represents the bottom plus the spherical part. And then we're going to have plus 2 pi r h, which is now 2 pi r times this whole expression, which is v minus 2/3 pi r squared. V minus 2/3 pi r squared over, I believe it's pi r squared. Yep. Pi r squared. So that's our whole expression for surface area. So to solve this problem, we need to figure out what our local minimum for surface area is, right? Because we want to basically have the least amount of surface area, the least amount of metal for the same amount of volume. So we're going to find the local minimum. And so, not sure what happened there. Minimums exist at critical points, basically. And so how we're going to find those critical points is we're going to be differentiating this with respect to surface area, I guess. And then we're going to be looking for minimas and maximas by solving for the roots of the derivative. But first, I want to simplify this a bit because I don't want to have to differentiate all that. Because yeah, with respect to r, I guess. But yeah, so I'm going to simplify this a little bit. So surface area equals 3 pi r squared plus, I'm going to distribute this out, 2 pi r v minus 2 pi r. Oof, okay, so this is 4/3 pi squared r to the power of 3. And then this is all just divided by pi r squared. So right away, we see some issues still that we can get rid of. So get rid of the r. This goes to 2. This one will go to r to the power of 1. Get rid of the pi here. Get rid of the 2 on that pi. And yeah, so I'm going to just simplify this once more. Saying surface area equals 3 pi r squared plus, I'm going to separate this into two fractions, 2v over r plus, that's a minus, 4 over 3r, and then we still have 1 pi and 1 r squared. And we can actually cancel the r squared. My bad. So it's just 3, because basically this squared will go there because I'm separating the fractions. So that's 3 pi, or 4/3 pi r. So now this looks a lot more manageable to differentiate because basically we have, besides this, we've isolated all of our r's to just be on the top where we can just use the power rule basically. So now I'm going to differentiate. So surface area derivative will be 6 pi r, because basically I just power ruled that, plus, this is a little more difficult, it's actually going to be minus because we're at the bottom, 2v over r squared. That's also power rule. We can think of this as to the power of 1, but it's on the bottom, so it's a power of -1 if it was on the top. So we're going to be multiplying it by a negative, and then this is going to go down by 1, so it's actually going to go to -2. So that's where we get that from. And then we have minus 4 pi r over 3. That just turns into minus 4 pi. This should have a... No, never mind. It shouldn't have a square. 4 pi over 3. So now with this, let me just verify my work here, because I feel like there should be a r squared here, if I'm not wrong. No, it looks valid. Pi r h, 2 pi r times h. Okay, whatever. Let's see how this goes. So this is our derivative, surface area. So we want to find where surface area prime equals 0. So the change is 0. So local max or local minimum. So at this point or that point. So when we set this, it'll be 6 pi r minus 2v over r squared minus 4 pi over 3. So right away, we see a little bit of a problem here because basically we have r terms on the bottom, on the top, and just r terms that are just everywhere basically. So this leads me to believe that something might have gone wrong, but trying to think, did I mess up differentiating this? I don't think so. 2 pi r, did I solve for that wrong? It'd be r4. Oh, I see my issue. So this has a 3 here. This should have a 3 here. And in that case, it would go from r3 to r4. So I'm going to go 4 down to 2. So that means this is squared. And that means that this would still have r, and this would actually turn into 8 pi r. And that means this would also be 8 pi r. So sorry about that. That's where my issue was. So now this makes it a little bit more manageable. So if we notice, we have things in terms of pi r here. So we can add the like terms. So I'm going to change this by multiplying 6 times 3, which is 18 pi r over 3 minus 2v over r squared minus 8 pi r over 3. So what we can do is we can subtract these two and say 0 is equal to 10 pi r over 3 minus 2v over r squared. I'm going to just write this on a new page. 0 equals 10 pi r over 3. I think that was minus 2v over r squared. 2 for r squared. So remember, v is just a constant, so it doesn't really matter. So now this looks a little bit easier. We can shove that on that side and get 2v over r squared equals 10 pi r over 3. Get rid of the r squared. We're going to multiply both sides by 2 times r squared, blah, blah, blah. Cancel the 10 and 2. That turns into a 5. So we'll end up getting v equals 5 pi r to the power of 3 over 3. But we're solving for r again because we already know what v is. That's just a constant. We're given that. We want what percentage of v is the r. So we're going to multiply v by 3. So then that basically equals, or as r, we just solve for r, we can divide by this, put that on the bottom, and then third root. So we got r equals the third root of 3v over 5 pi. So now, does this really help us? Not quite, because basically we want to know how v and h compare, or sorry, r and h compare. And so we've solved for r, but we need to go back now and solve for h. So I'm going to change to red for our h equation. So basically, now that we know what r is, we're going to plug that into h to figure out. So h equals v minus 2/3 pi r to the power of 3 over pi r2. So actually, I'll just clear the page right here. So h equals v minus 2/3 pi r to the power of 3. So r is the third root of, I believe it was 3v over 5 pi. And then this is all divided by pi r squared. So it's pi times 3v over 5 pi, and then to the power of 2. So now this looks a little bit more manageable. This is also the third power. Forgot to include that. So now all we have to do really is just do a lot of simplifying to see how they compare. So what we can do first is distribute this. So basically the third root cancels. So h is equal to v minus 2/3 pi times 3v over 5 pi, right? And then we have pi times this, which is just, I'm going to distribute this out to be 3v over 5 pi times 2 over third. Because basically it's just, yeah, that's 1 over third, and that's 2 times 1 over third is 2/3. So now what we can do here is we can start canceling some stuff. So there's 3 on the bottom, pi there. So basically it's v minus 2v over 5 over pi 3v over 5 pi to the power of 2/3. So we know that v is the same as 5v over 5. So we can combine these two things, and 5 minus 2 is 3. So I'm going to clear this just to have more writing room. So basically, we can simplify this down to h equals 3v over 5. divided by a lot of stuff. So 3v over 5, and then we can multiply this because there's only one term by all this crap on the bottom. So that's pi 3v over 5 pi to the power of 2/3. Okay, so now this looks a lot better. So we have some 3v's over 5 pi's, and we have all this crap. So I'm going to separate these fractions and flip them around. So this is equivalent to 3v. I'm going to separate this by saying 3v to the 2/3 over 5 pi to the 2/3, right? And then basically if we're dividing by something, we can flip that part onto the top. So 3v times 5 pi to the power of 2/3, right? Because this part got flipped over because we separated the 2/3 out, divided by 5 pi times, and we still have on the bottom 3v to the power of 2/3. So now what we can do basically is we can start canceling out, because this is basically to the power of 3/3. This is to the power of 3/3. So 3 minus 2 is equal to 1/3. So 3v to the 1/3. And basically 2 minus 3 is -1. So we can just put that on the bottom. So that's 5 pi to the 1/3. And if we look at this, this is equivalent to the third root of 3v over 5 pi. And that is equivalent to h. And if we remember, r is also the third root of 3v over 5 pi. Oops. So basically, it's saying that the radius and the height of the silo would be exactly the same. So here, I'll try and draw that silo to the best of my ability. So if we have that, that's ugly, but not going to get it. It's only going to get worse, I guess. Okay, good enough. So here's our radius of our silo. It's going to like go up like that. It's not a perfect circle. Doesn't really matter. And the h will make this a perfect square, basically. Like, oh my god, that's horrible. But like this part is basically a perfect square. So essentially this is the optimal silo for volume to surface area. So basically, if you're trying to store your like a certain amount of corn and you want to use the least metal, this is the shape that you're going to use. Obviously, we don't see silos that look like this. Probably has a little to do with that people don't want to take up as much room in the wide way as like up, because like, you know, the sky's upwards and like land is valuable, so they probably don't want to be making these like squat silos. I think we see silos that look more like, okay, I'm not going to draw that, but they're more, you know, like tall than like they are wide. I think that's mostly to maximize land, and you can check like what the maximum is. I guess it would be like one of the endpoints, like infinity. So we could take a limit of our original equation of SA as it approaches infinity to see what like the minimum is. But yeah, so that's basically gonna be it for this video. So hope it was somewhat helpful, and comment if you want me to try and solve problems for you or something. So yeah.